In this segment, we're going to get hands-on with the code and see what querying the language model actually looks like. So I've loaded everything up here in Replit. So we've got the two Python files, main.py and bigramlm.py, as well as the two data files here. So let me show you what I did so far. So first, I imported everything from main, and then I called read data and read it into this tuple of train, test, where train is a list of strings and test is the same thing. So we've read these files, we've read in about 25,000 lines of text. So then I called estimate bigramlm on the training set, and that takes a second, but it does our process of counting up all of these counts that we need in order to compute probabilities. The next thing I did after that was check normalization on the language model. So remember that we talked about the language model as a probability distribution over the next word given these previous words. And what that means is that for a previous word, the sum of the probability scores associated with each possible next word has to sum up to 1. So what we do here is we check normalization on after 3 different possible previous words. So the, asked, and did. And what we do here is we define this total probability to be 0.0, and then we loop over every word in the vocabulary. And we ask the language model what the probability of that word is given the kind of fixed context word, which here is again one of these 3, the, asked, or did. And then what we do is we see, is that total probability very close to 1.0? And over here, we can see that for these 3 different contexts, when we sum over every word that we've seen in the vocabulary, we get 1.00000001172 for these. So floating point arithmetic is a little bit tricky. There's going to be rounding errors and things like that. But we're adding up all these values, and it gives us something that's very, very close to 1. So this gives us confidence that what we have is really a probability distribution because it sums to 1. OK. So let's see what we can actually do with the language model. So then I called query lm, which is what actually will print out some top words and probabilities for something coming after a given context word. So here I asked it about and the most likely next words were the, with probability 0.08. So actually a pretty small probability. Unc, this is an unknown word placeholder in this data set where they've basically replaced words that are pretty rare with this, with this placeholder. A, was, and quotation mark are the next 3. Okay, then I asked it about the, and it gave some kind of similar stuff where unc is also up there. But interestingly, first and united both have pretty good probabilities. Probably because we see the United States fairly often. I asked it about John, and here there's a kind of interesting, you see unc again, John apostrophe S, so we're often talking about John's something. And then we have Constantine in here, and if you look in the actual data, it turns out John Constantine is a fictional character that occurs a decent amount in this slice of Wikipedia. So this goes to show that this data is not necessarily representative of the whole English language, but instead it's just this kind of one slice that we saw here. And then I did it with bad, and what the kind of interesting one I think here is that weather is very high probability. Okay, so that shows you the basics of these kind of querying operations. So what we looked at here was what query lm and check normalization can do, and how to load and query the model here. So turning to the stuff that you'll be building, we have a function here, getBestWord, which takes an lm and a context and is supposed to return the most probable next word. So you can use this getVocabulary method on the language model to get the possible next words. And then you want to loop over each one and call lm.getProbability to check its probability. And then you'll keep track of the best word and its probability in your loop. And if you see one with higher probability, you kick them out and store that one. So you'll want to use some local variables for that. All right, and then we've given you getBestSentence, which repeatedly calls getBestWord and is going to generate a whole sentence. This will just kind of go for a while. If you want, you can stop it when you get to punctuation, but you might see that that actually doesn't happen that frequently, so it's up to you whether you want to explore that or not. All right, so then you can often get more interesting sentences by sampling. So instead of taking the most likely next word, take a random next word. So sample word gets repeatedly called by sample sentence in order to do this, but how does sample word work, or how is it going to work? So the first thing that we need is a random number, which we can do by importing random, and then calling random.uniform 0, 1, which returns a random real number from 0 to 1. All right, so then we need to actually turn this into a word which involves looping over the probability distribution for the next word. Okay, so I kind of have a sketch here of the probability distribution conditioned on something. This is fictitious, it's just for the purposes of the slide. But we've got these probabilities associated with these words. So what we do is we are going to define x to be our random number, and suppose our random number in this case was 0.51. What we're going to do is we're going to loop through these words and their probabilities and find the first word where the sum of the probabilities so far is greater than 0.51. In that case, it's this of here, because if you take 0.25 and then add 0.1 for a, it's 0.35. That's still less than 0.51. Then we go on to of, we add 0.2, and now it's 0.55, and that's greater. All right, so we sum those up, and then we say, okay, we're going to stop here and return of. So the question is, does this actually kind of correctly draw a sample from this language model? So I want to think about just the first word, the, here. And imagine that your sample, which again is a random number from 0 to 1, if it's less than 0.25, this criterion is going to kick in immediately, right? It's less than 0.25, so we take this 0.25, we say, okay, x is less than 0.25, so just return the. So it turns out you have a 1 in 4 chance of doing that, because if you get x even slightly larger, like 0.26, then you're going to go on to the next word. So then we'll get the second word if x is greater than the probability of the first thing, but less than or equal to probability of first plus probability of second. Because if x is greater than 0.35, then we're going to move on again, right? So hopefully you can convince yourself that this is kind of correctly mapping from that random number to a random word from this probability distribution where each word sort of has the right probability of getting picked. Okay, so once you implement these, you can try some different contexts, see what the samples look like, and just sample sentences a whole bunch of times and see what happens. You'll get an idea for kind of how this language model works, what some of the things it does maybe well at, or when it produces something that's kind of interesting, and when it works maybe somewhat poorly. That's the end of this segment.